To recapitulate just a little bit where we are and how we got there, we recall that we can measure force versus slope m. We're going to use m for slope, which is a little ambiguous because in a minute we're going to talk about mass. But force versus slope, we get a nice linear relationship. The graph crosses the slope axis, and actually I've got that wrong. That's crossing the slope axis down below, or out in front of the force axis. Let's not worry about that for right now. Anyhow, you get a linear graph of force versus slope m. You also have a linear graph of acceleration versus slope m. The fact that these two are linear means that if you want to do force versus acceleration, it's going to be linear. And we saw that the graph is linear and it comes very close to the origin as we would expect. So that we make the conclusion, or we come to the conclusion, that force is proportional to acceleration. We call mass the proportionality constant between force and acceleration. Okay, so this is the relationship that we have. We also note, just by analyzing the graph of v versus t, if you have a trapezoid between two clock times, the delta s, the change in position versus those times, or between those times, or the displacement between those times, is represented by the area under the graph for reasons that we've seen amply. And this graph represents the fact that delta s is the average velocity multiplied by delta t, one of our two fundamental equations of motion. This graph shows that the acceleration is the slope of the velocity versus time graph. If you have a delta t here, that's the run of this trapezoid. The rise is your delta v, and the slope is your rise over run delta v over delta t, or your acceleration. And this tells you that the final velocity, the velocity you have at this end of the interval, is equal to your initial velocity, which is the velocity you have at the beginning of the interval, times the acceleration times delta t. That is the rise of this graph, which is your delta v, because delta v equals the slope times your delta t. So that this picture corresponds to the fact that Vf equals V naught plus A delta t. And these are our two most fundamental equations of motion, from which we obtain two others. And then we have the following set of relationships. Okay, we have F equals ma, as we saw. From the two fundamental equations of motion that we mentioned here, we eliminate delta t and we obtain this fundamental equation. If we then substitute for a the quantity F over m, we can relate initial final velocity, displacement, force, and mass by this equation. Turns out that we can solve this equation for F delta S, which is a quantity that we call work, the delta W, the work contribution over this displacement, and we call 1/2 mv squared kinetic energy, so we have final minus initial kinetic energy. So in a uniform acceleration situation where F, again, stands for the net force acting on the object, the work done by the net force is equal to the change in the kinetic energy of the force. And that's the first version of a work energy theorem.